Alright, we're doing problem number 12 of chapter 28 of Physics for Scientists and Engineers by Knight, second edition. I think this is a great conceptual problem. It's a good way to break down the left-hand side of Gauss's law and really understand what's happening here with this dot product and our enclosed surface. The problem states a 2 centimeter by 3 centimeter rectangle lies in the xy plane. Okay, so this doesn't really have to be respective to the xy plane. Just whatever, let's just draw it. As long as we have the area. 2 centimeters, 3 centimeters. Okay, and we're to find the electric flux through this enclosed surface under these two conditions. And I think what I want to do is let's talk about this E field within this enclosed integral here. They give it to us in vector notation, but really this is a constant, just with different vector components. So it's continuous throughout. It's not a function of a distance from a point or anything like that. We can draw this vector. The scale doesn't necessarily matter. This is just representative, but we can say 50 I hat. So let's go 50 in the I hat or x direction, and then 100 in the k hat direction. So let's go a little bit longer in that direction just to show for representation. Alright, and then the sum of those two vectors means you have a field. Let's make that a different color. Maybe green. Let's try green. Kind of a vector in that direction. So everywhere you've got this happening, alright, going through our two-dimensional surface. But let's talk about what this dot product means. Okay, so when you take a dot product, you find the product of like components and then add them up to get a scalar. Within this enclosed surface, what we really mean is we're interested in what's going through the surface. So what is the component normal, okay, normal to this surface? Well, it's going to be, since this is in the xy plane, it's going to be in the z or k hat direction. So really we're only interested in, if we're going to break our E field up into components, we're only really interested in values in the k hat direction. Alright, so we can really ignore this 50 I hat because it's, if we look at what we'd be multiplying it or dot producting it with our surface, we're looking at 0 I hat plus 0, let's make it a hat, 0 j hat plus 1 k hat. Okay, that would be like the unit vector of this normal to our surface. So if we were to multiply 50 I hat times 50 I hat, that would just go to 0 I hat, and then after you add them all up, you would really only be left with k hat at 100. That's in newtons per coulomb, by the way, so we'll start writing that. So really, since this is E is a constant value, it's not a function of anything, we can move it out of the integral, understanding that we're only focusing on the normal vector to the surface. So we can say that here our flux equals our E field in the k hat direction, we do that, times the surface, alright, our surface in question here, dA. Understanding that really this is representing, if we integrate that, we're just going to end up with A, the area. Okay. So what is our area? Our area would actually be our 2 centimeters times our 3 centimeters. So we can say 2 centimeters times 3 centimeters, alright, which is equal to our area. So we could plug in some values and progress in this equation here. Our flux is going to be equal to 100 newtons per coulomb times our area, which let's just convert that to meters. That would actually be, I'll use this area over here, 0.02 meters times 0.03 meters, which ends up equaling 0.00, double check my numbers, 06 meters squared. Alright, so we can plug that in over here, 0.0006 square meters. Alright, and our flux ends up being 0.06 Newton meters squared per coulomb. Alright, for part A. Part A. That's our answer there. Alright, so let's look at part B. Part B is just changing the direction of our E field. So let me see if I can not destroy this drawing too much, just to kind of illustrate the point. We're going to go 50 in the I hat direction plus 100 in the J hat direction, which is that there, and so the sum of those two vectors would be something, let's go back to green, something like that. Alright, well, we need to remind ourselves of this dot product here, and we're really only interested in what is normal to our surface that actually passes through it, which is the k hat vector. Since this does not include a k hat vector, we can assume that it would actually be 0 k hat, and so when you'd have 0 k hat times your area, okay, we could actually just write that down here, part B, 0 newtons per coulomb times 0.0006 meters squared, okay, because that's our k hat, ends up being 0. Alright, 0 Newton meters squared per coulomb, because there's nothing normal to the surface. Alright, so those are the answers and explanation of problem number 12. I hope that answered any questions anyone has.